So the next presentation is by, I hope I can pronounce this correctly, Ilario Gelmetti. Thank you. Gelmetti is from ICIQ, and his presentation will be about the relevance of the energy alignment shift in organic semiconductor Perovskite interface and the influence in the open circuit voltage. Thank you.
Okay, so thank you for the nice introduction. Just a sec. Okay, yeah, Nuria could not be here today, so I'm going to deliver her presentation, and which is about the relevance of an energy alignment shift in organic semiconductor perovskite interface and its influence on the open circuit voltage. So we are both from Professor Emilio Palomares in Tarragona, which is still in Catalonia, and, well, in ICIQ. So, basically, this place. Okay. So, we are not yet into the stability, sorry for that, but we are still trying to understand the basic physics in the perovskite solar cell, as we think that we still have to get it right. So we started asking ourselves why some whole transporting material works while some other doesn't. So how can we understand which one will work in a predictive way? So we think that we still need some insight on the fundamental physics, and our probe are optical and electrical transients. So for example, one of the first techniques that we use is the charge extraction, which basically is we take a full device, we illuminate in open circuit condition, then suddenly at the same time we short circuit it and we switch off the light. So we try to extract as fast as possible all the charges contained in the device. So we obtain a voltage decay, measuring with an oscilloscope through a small resistor. So we obtain this decay, we can convert the voltage profile to a current profile knowing the small resistor, we integrate in the time, so we obtain the area, so the charge that was extracted. We repeat changing the initial background light intensity, so that we observe the charge stored in the cell at different open circuit voltages. And that's the result of the technique. As you can see, when there is a linear part that we can interpret based on the geometric capacitance, which is basically like if the cell was working as a parallel plate capacitor. So the charge stored is just proportional to the open circuit voltage and represents when the charges are stored in the electrodes. When the electrode starts to get saturated, the charges starts to get stored in the bulk of the material, so in the perovskite, and we can see an exponential part, which basically the shape just depends on the Fermi-Dirac distribution in the material. Okay, so the geometrical capacitance, the information that we can take out from it is, well, basically the layer thicknesses and the dielectric permittivity of the layers, which is just the parallel plate capacitor physics, and the charge, the contacts, the selective contacts charge accumulation capability, which mainly depends on the doping density, if the doping density is enough. Okay, from the exponential part, so the chemical capacitance, we can have information on the position of the energy levels, the doping density, and the density of states of the layers, and we can be affected by the recombination. So for studying the recombination, we use the transient photovoltage, which basically consists in a cell kept in open circuit condition, measuring the open circuit through an oscilloscope. Well, also here the graphic lacks a connection. Well, so we shine a constant light intensity and we add a small perturbation through a laser pulse. This small perturbation produces a small amount of extra charge, which will be observed as an increase in the open circuit voltage. So the open circuit voltage will grow, and when the light pulse is over, it will relax to the steady state condition as it was before the light pulse. This dynamic can be fit usually by an exponential decay and can give information on the lifetime of the charges, at least from our interpretation. Okay, so this is the lifetime of the charges plotted against the charge the amount of charges stored in the device that we obtained from the previous measurement, so the charge extraction. Okay, from these graphics we can obtain the charge lifetime at different light intensities. For example, the last point will be the one sun intensity. And the recombination order. In perovskite solar cell, the recombination order is still unphysical, so in this case was close to 12. So the correct interpretation is still lagging behind. Anyway, other techniques that we usually use but will not be used in this presentation is the differential capacitance, which is basically can give the similar results to charge extraction. And with these techniques we can obtain the capacitance, observing how the voltage changes, adding a small extra charge with a laser pulse. And the laser transient absorption spectroscopy that is quite popular and it can observe on a wide range time ranges, charge injections and lifetime of many of the excited species present in the wall structure, and basically observes how the absorption changes after a laser pulse. And then the time resolved photoluminescence that was mentioned also from other presentations, where we can see the radiative recombination and in an indirect way all the processes that suppress the radiative recombinations. Okay, so for having some insight of what's happening there, we try to change as little as possible. So we changed just the HTM, keeping everything else the same, trying to have the same thickness of the whole transporting material. So we obtained this TE1 from Nazario Martin group in Madrid, which is basically a very similar structure of the spiral OMTAD one, but has a different core. This makes it easier to synthesize and cheaper. Well, and also we were interested by it because it showed from cyclic voltammetry a deeper HOMO level. So we thought deeper HOMO level, we can obtain higher open circuit voltage. Could be interesting to try. Well, unexpectedly, we obtained a lower open circuit voltage, even if the mobilities were just 5 times smaller, so still acceptable. And so we got curious about why we expected higher voltage and we obtained lower voltages. And the efficiency obviously is resulting to be a smaller value. But okay, we are interested in voltage mostly. Okay, so we used the transient photovoltage for studying the recombination. And we saw that the lifetime obtained from the spiral OMTAD is even smaller than the one obtained by solar cells with the new whole transporting material. So that's not the reason for a lower open circuit voltage. Then we observe the charge extraction, and we are interested, well, the first part just says that the thicknesses are the same, okay, not interesting. The exponential part, which is enhanced here, showed a shift in an unexpected direction of the exponential part. So this shift indicated that the spiral OMTAD HOMO level was closer to the valence band maximum of the perovskite, while we expected from the HOMO level calculated from cyclic voltammetry the opposite. So we expected the TAE1 HOMO level to be deeper. So these exponential parts should start later at higher voltages. So we saw no recombination change. We saw this shift in the wrong direction. So what we thought is maybe the HOMO level calculated by cyclic voltammetry is really wrong when the layers are deposited on top of perovskite. As you can see, we are using a cesium for neodymium methylammonium, so this tripole cation perovskite. So we thought maybe there is a shift, and this shift is much bigger for the spiral OMTAD than for the new molecule. So the resulting HOMO layer is closer to the valence band maximum of the perovskite for OMTAD rather than for the new whole transporting material. This could explain why we have this unexpected VOC change. Well, we thought, how can we confirm this hypothesis? So we started collaborating with with people from ICMAB in Barcelona, and who are very professional, and they are also here, I think, today, in measuring Kelvin probe force microscopy. So with this technique, we can know the work function, which is the difference between the Fermi level and the local vacuum level of a surface via a technique called contact potential difference. And we saw a bigger shift when the spiral OMTAD is deposited on perovskite rather than on titania, compared with the shift that we observed with the novel molecule when layered on perovskite or when layered on titania. So we observe this bigger shift, and well, this is what we expected. So there is bigger shift, so the spiral OMTAD level managed to get closer to the valence band maximum of the perovskite when layered on perovskite. Okay, so for further confirming this, we started studying other similar compounds, still from Nazario Martin group, which also in a case they presented the same HOMO level, in a case a deeper HOMO level, and we still observe a lower open circuit voltage. And we are waiting, well, for what regards the photophysical studies, we still observe a shift in the exponential part to lower voltages for the novel molecules. Well, this is quite noisy anyway. But in this case, the lower voltage could also be caused by a higher recombination. As you can see, at the same charge amount, the recombination of the novel molecules is quite faster. So we are now processing the results from Kelvin probe force microscopy for see if we can confirm our hypothesis also with these molecules. So in conclusion, these three molecules were designed to replace spiral OMTAD for cheaper and easier synthesis and for having a deeper HOMO level, so hopefully a higher open circuit voltage. A shift in the whole transporting material HOMO level could cause the observed shift in the exponential part of the charge extraction. This was verified by Kelvin probe force microscopy, measuring the surface work function. And this new HOMO position on top of the perovskite could explain why with this novel whole transporting material we obtained a lower VOC, and could explain why with spiral OMTAD we have still better efficiencies and better VOC. Thanks.
Thank you. Okay, we'll go for a few questions. Thank you.
Very nice work. Has anybody tried to do these measurements using UPS?
Not yet.
Yeah, that would be interesting to compare, because with UPS you can deposit one layer at a time and really observe, the shift,
Yeah, we will know the real HOMO and the real.
Exactly.
Yeah, that's needed. We have to do it.
Thanks.
We know. Thanks.
There's room for another question. Yeah.
There is a discussion if this large capacitance at the high voltage is really like a Fermi level approaching, so that you would see accumulation in the material and identifying the energy levels. It can be also some surface polarization, so that you can form a junction, and then it's not so clear how the capacitance is correlated. You have make a model of a HOMO junction here or something. So this has to be discussed also.
Actually, I did in collaboration with Jenny Nelson. And I think that you are referring to the results you observe in the impedance spectroscopy at low frequency.
No, I am referring to your capacitance.
Yeah, but in our case, the capacitance is not that big. So we're not observing that same effect.
Why do you call it chemical capacitance?
Because the correct name is like quantic capacitance. Is basically because we call it chemical capacitance because it's caused by the chemical potential of electrons stored in the bulk of the material.
How do you know it's not a junction capacitance?
Well, we don't know.
Thank you.
But it's the easier hypothesis. Yes. So if we can avoid to introduce more physics.
But this is a complex point.
Yeah, could be.
That was the famous answer again, the short one. That was, I don't know, that was the famous answer again. Good, let's thank the speaker once more.
Thank you.
Now we go